All right. So as I mentioned, the goal of this part of the course is to talk about the nonlinear solutions of the Einstein equations that you have already seen. So the Einstein equations, g mu nu equals 8 pi g t mu nu, and the goal is, so our goal is to study nonlinear solutions of this equation. Now, this is a nonlinear system, and usually it's hard to find analytic solutions for nonlinear system of equations. So therefore, in order to find analytic solutions, we usually make some approximation, some assumptions, simplifying assumptions. So here, now we want to make the following assumption, that we want to consider solutions with a spherical symmetry. Furthermore, so this is one assumption that we are making. Furthermore, we study vacuum solutions of this equation, which means that T mu nu is equal to 0. So now it turns out under these two assumptions, we can find an exact solution of these equations, which is called the Schwarzschild metric. And that's a very important solution of these equations. So let us go through it. I'm not going to derive everything. I just tell you the main ideas, and then you can see the details in my notes or in the books in the textbooks that I mentioned. The assumption of a spherical symmetry leads to a simplification of the form of the metric. So what does it mean that we want to solve this equation? It means that we want to find a metric, because as you have probably learned, in Einstein theory of gravity describes gravity in terms of relates gravity to a space-time or space-time curvature. That's the content of these Einstein equations, and this can be thought as being a differential equation, a partial differential equation for the metric. So the goal is to find a metric, g mu nu, little g mu nu, and that we can represent it by the line element. So we have ds squared, the line element, and this line element, under the assumption of a spherical symmetry, it can be written in the following form. So now I'm writing the most general form of a spherically symmetric metric. Where this piece, sometimes I'll call this piece just the omega square. So now the question is that first you can ask, why is it the most general form? of a spherical symmetric metric. But basically, when we say it is a spherical symmetric, it means that we can identify some spheres which are symmetric. So different points on these spheres are not distinguishable from each other. So that's what we have done. We have identified those spheres here. So these are the spheres that identify, and this is the unit metric of the sphere, a two-dimensional sphere. And then we have chosen one of our coordinates and called it R. And this coordinate, it characterizes the area of these spheres. So the area of these symmetric two spheres is determined by this coordinate R, is equal to 4 pi R squared. So of course, this is something that you are familiar with from just Euclidean geometry. So now if I consider Euclidean geometry, by which I mean just R cubed, the three-dimensional Euclidean space, then you know that the metric which we can write as dx squared plus dy squared plus dz squared, you can also go to the spherical coordinates and write the metric as dr squared plus r squared d omega squared, right? And then you have the same relation for the area of the sphere, 4 pi r squared. Now, it happens that in Euclidean geometry, so let me try to also draw a picture. If I consider a sphere here, this coordinate r, r is also this is describing the distance from the origin. However, this is a particular feature of the Euclidean geometry, the fact that r is the distance to the origin. That is not going to be the case generically. But what r is, apart from being the distance, is that it is describing the area of the spheres. So now let us consider a different example, a three-sphere. So what is the metric of the three-sphere? The metric of the three-sphere in the same coordinates, by the same coordinates, I mean the coordinates in which I pick a set of symmetric two spheres and then call the area or describe the area by a variable r or related to a variable r. In these same coordinates, it can be written as dr squared over 1 minus r squared plus r squared d omega squared. So now this is a little bit hard to draw. So in order to draw it, I go to one lower dimension. So instead of instead of drawing a three-sphere, I'm going to now draw a two-sphere. Oops. What did I do? and then give you the idea. So let's consider just the two sphere, and then let us pick a point which I call it a north pole. So this is the north pole. So imagine this two sphere can be the surface of the Earth that we approximated by a sphere, and I pick a point and call it north pole. And then I consider points that are at a fixed distance from this north pole. Now, if I'm on a two sphere, these slices will be just circles, right? On the surface of the Earth, these are what we call the latitudes. But now you need to have some imagination to go one dimension higher. So imagine now this is, instead of being a two sphere, it's a three-dimensional sphere. And then I pick a point in that and do the same exercise. Now these slices that I'm going to get, instead of being circles, they are gonna be two spheres, whose metric is now given by this part. So this part will describe the metric along these two spheres. Now we are imagining that this is a three-dimensional spheres and these are two spheres. And this is the metric of that part. And then now we can see that for a three sphere, what happens is that R is no longer R does not describe the distance from the North Pole. Okay, now I can give a little exercise and ask you to exercise what is the distance on three sphere, which is S3, on this on S3 between a point at R and the North Pole. Okay, so can you try it for a few minutes?
Sorry, can I ask you a question before the exercise, please?
Sure, yes.
Okay, could you please re-explain the concept of what the lines of latitudes are doing there? Because I don't really get that. And the second question is, if the lines of latitude...
Sorry, I didn't, can you repeat the first question again?
Okay. My first question is, could you please repeat the concept of what the lines of latitudes are doing in the diagram you drew over there?
Uh-huh.
And the second question is, if the lines of latitudes were to be replaced by the lines of longitudes, would the same thing still be applicable in that instance?
Uh-huh. Okay. Okay. So the latitudes are. So what are the latitudes again? So I pick a point so let's go to two sphere for simplicity. So like imagine the surface of the Earth is a two sphere. I pick a point on the surface of the sphere just arbitrarily, because all points on the sphere are the same. It's maximally symmetric. So I just arbitrarily pick a point and call it the North Pole. So this is my point. And then I consider all of the points on the sphere that are at the same distance from the North Pole. Right? So for instance, I consider points which are at distance, I don't know, let's say this is distance 0.1 from the North Pole. I consider all of those points. Those form on a two sphere, those form a circle. And that circle, I call it the latitude. The latitude at r equals 0.1. Then I go to point r equals 0.2, for instance, and then I consider all of the points that are at distance 0.2 from the North Pole. Sorry, I said it wrong. Okay, again. I pick all of the points at a given distance, at a fixed distance from the North Pole, say at distance 0.1. And then I pick all of those points, they become a circle. Now I measure the circumference of that circle, right? And this, so here I pick all of those points that are at a fixed distance from the North Pole. I measure the circumference of this circle and divide it by 2 pi and call it r. R corresponding to that latitude. And then I repeat this. Now my claim is that the metric of the sphere can be written in this form. In the case of a two sphere, it will be, so let me just here say, in the case of a two sphere, this metric is gonna become ds squared equals dr squared over 1 minus r squared plus r squared, say, what do we call it, d phi squared. So this two sphere has only two, it's a two-dimensional manifold, so it has two coordinates. Now, once we go from two sphere to the three spheres, then the same idea can be applied, except that now we get this metric where here the omega squared is a metric on a two sphere. So the omega squared is given by this expression here. Did I answer the question?
Yes, the first part, but the second part.
So the longitudes are different concepts. So the longitudes are defined in a different way. How are they defined? The longitudes are, so if you pick a North Pole, the longitudes are all of the great circles that pass through the North Pole. So those corresponds to this. So these great circles are what? These are, okay, so let me just, maybe I should have used a different color for them. So these are the longitudes. And these are geodesics, these are great circles. While latitudes are not geodesics. They are just defined as I did it. They are points which are at a fixed distance from the North Pole. Did I answer the second question?
Yeah. But there's a part which I said that even though the longitude they runs from north to south, can they be used to actually derive what you derive with the lines of latitude?
Well, no, I mean you can use them to give a different coordinate system for the sphere, but that will be a different coordinate system. So you can label longitudes by a variable called theta, or yeah, let me think for a second. Yes, so yeah, what longitudes do is that basically they are lines of constant phi. So right in this metric that I use, longitudes corresponds to phi equals constant, while latitudes corresponds to r equals constant. Okay, so can you now think about this problem? Are there other questions?
I have a question. So the variable r, what does it represent in this for three sphere?
R represents the area of these two spheres, meaning that the area of a two sphere at radius r is 4 pi r squared. Because if you we have here the metric of a two sphere, right? So the omega squared is d theta squared is d theta squared plus sine squared theta d phi squared, right? Now you can now integrate, calculate the volume of this manifold. So now, since it is a two-dimensional manifold, the volume of it is actually an area. So you can calculate the area of this manifold. This is a unit sphere. So if you calculate integral d omega, which is actually integral d theta d phi, the square root of this metric. So here let's call it GS2 mu nu dx nu. So if I calculate integral d theta d phi, determinant of GS2, that integral is equal to d theta d phi sine theta. And to be more specific, here theta ranges from, okay, let me do it this way. So here theta ranges from 0 to pi, and phi ranges from 0 to 2 pi. So this integral gives me 4 pi. So 4 pi is the area of a unit two sphere. And now if I'm saying that I have points which are sitting at a constant distance from the North Pole, and the line element is given by r squared d omega squared, then I will get the area of those that two sphere to be, I go through the same exercise, except there is except that the square root of g, or determinant of g, will be equal to now r squared sine theta. So this area becomes 4 pi r squared. So that's what r represents. If you try to calculate the area of those that two sphere that sits at coordinate r, the area will be given by 4 pi r squared. This is similar to the statement that if you go to the two sphere and try to calculate the circumference of a latitude at radius r, the circumference of that latitude will be given by 2 pi r. So the same way that the circumference of a latitude defines, or r is defined in terms of the circumference of a latitude, here r is defined in terms of the area of those generalized latitudes. Okay, other questions?
So that means at the North Pole, R is 0?
Yes, yes. Well, maybe one thing that you can try to do for this exercise is to relate this metric to the more standard metric for the three sphere. So what is the more standard metric for a three sphere? It's kind of similar to the metric for a two sphere. So this was the metric for a two sphere, right? We write them in terms of angular variables. So now how do we write the metric for a three sphere in terms of angular variables? It's very easy. We just generalize this. Every time we go one dimension higher, we add one additional angular variable that ranges from 0 to pi. Let me move this down. So what can we do here? We can try to relate this metric that we have here, relate this metric to a more standard metric for a two sphere, which now I'm sorry, for a three sphere. So now I introduce a new angular variable where now chi is ranging between 0 and pi. Or if you wanted to write it, if you want to write it more explicitly, it is sine square chi d theta squared plus sine square theta d phi squared. So if we can connect relate this metric to this metric, then perhaps it is easier to determine the distance between the point R and the North Pole. Because here, so what is the location of the North Pole on this metric? Any idea?
Chi equal to 1 and theta and phi are 0.
Chi equals to 1. Why?
Oh no, chi is also 0.
Okay. Yeah, so why is that the North Pole? It is the North Pole because the North Pole corresponds to R equal to 0. And so here there are so at the North Pole we have here R equals to 0. That's the point when the area of this, the size of this this latitude shrink to 0 at that point, right? Now here, if I want the size of this latitudes to shrink to 0, I want this sinus square to be 0, which happens when chi is equal to 0 or chi is equal to pi. So indeed, chi equal to 0 is the North Pole and chi equals to pi is the South Pole. At both of them, the area of this latitude shrink to 0. So chi equal to 0 is the North Pole. And then the question is how do we relate? So this here, the theta and phi variables are the same between these two metrics. This the omega squared that I have written here and is basically the same object that I have here, or I have here. So the question is, what is the relation between chi and r? So what is chi as a function of r? If we know what is chi as a function of r, then we can determine the distance. How do we determine the distance? Because in this metric, determining the distance between 2 points is very easy, because this chi variable is actually measuring the distance here. So the same way that r variable here is measuring the distance in the Euclidean geometry. So if you find chi as a function of r, you are basically done. You know what is the distance between the point r and the North Pole.
So it's only arc sine of r.
Chi is equal to arc sine of r. Yes. Why? Because this factor here is r squared. The area of the latitudes. And then from here, it follows that the chi squared is the r squared divided by 1 minus r squared. So in fact, that's how I got this metric here. Now, one thing to notice, let me ask first, is it clear? Any question about this?
I have one question from the previous part when you wrote down the maximally the most general spherical isometric metric.
Okay, maybe. Yeah, maybe you can ask, but I might postpone the answer but yeah, let me know what is the question.
The question is, you didn't consider any coefficient for r squared d omega square. I mean, for the other terms, you considered coefficients which depends on t and r. But the r squared d omega square term had no coefficient in front of it.
So you are talking about this term here.
Yes, I was just saying, if can we consider some function which depends on t and r?
Well, no, this is exactly the point here. I chose r variable to be describing the area of these symmetric spheres. So that is my coordinate choice. That's my definition of r, if you like. Is the variable in terms of which the area of the sphere is 4 pi r squared. Of course, you can choose other coordinates, and then something else will sit here. But my choice for r, my choice of coordinates is that, so as you have learned, you can use different coordinate system as long as they form a chart. As long as they are single value, you can choose different coordinate system for your manifold. So here is my choice. I choose the size of the sphere, or some variable that is related to the size of the sphere. Now, this variable, this is a very good question, very relevant for the comment that I wanted to make. This variable, as you can see here in this metric, it might not be a good variable to describe the whole manifold, because as you can see here at r equals 1, this metric becomes singular. So it's a good choice to describe what is r equals 1. R equals 1 is actually corresponds to the equator of this the equator of this this manifold. And what happens at that point? There is no real singularity. The manifold is smooth at r equals 1. The only thing that happens is that the coordinate r, which was the size of this latitude, is not single valued, it's double valued. So therefore, it's not a good coordinate system to cover the entire manifold. I'm here talking about the 2 sphere, but the same is true for a 3 sphere. So while these coordinates are good coordinates to describe the entire manifold, this one is not good. You can describe either the either the northern hemisphere or the southern hemisphere, but you cannot describe the full manifold. So similarly there, I made the coordinate choice here. I chose r to be my variable, the size of this sphere. We might encounter some coordinate singularity because of this choice of variables. In fact, we will encounter it if we just consider the vacuum solution. But that will come later. Okay, other questions? Okay, now let us continue with this metric. Let me see if I can insert some page in here. All right, so we made this choice of coordinates here. For a spherical symmetry, for a spherical symmetric space-time. Now we can make another simplification by a good choice of coordinates. What is this other simplification? We can do a reparametrization of our time variable t. So we can take t, replace t by some function of t and r. In order to make this part of the metric diagonal, the TR part of the metric diagonal. So how do we do that? If I make this replacement, then what happens is that dt becomes or let me do it different. dt goes to dt of f times dt plus dr of f. So I'm not dropping the arguments of f. And therefore, dt squared goes to dt of f squared dt squared plus dr of f squared dt dr. Dr squared plus twice dt of f dr of f dt dr, right? Then we have dt dr that goes to dt of f times dt dr plus dr of f times dr squared. Now, I can make a good choice of this function f. I can make a good choice of this function f so that I eliminate this TR part of the metric. So how do we do that? If I plug in these two expressions in here and then require that the coefficient of the TDR vanishes, then I will get the following equation. So that requirement that GTR is equal to 0 after this coordinate transformation, it tells me that dr of f has to be equal to k, and now let's restore this variables. Dr of f of t and r has to be equal to k of t and r divided by h of t and r. So remember k and h were two of these unknown functions that we had here. Now I'm saying by a good choice of time variable, we can eliminate this TR part of the metric. So now after this, the metric is going to look like the following. So now this squared will be diagonal. And it is convenient to write these diagonal elements as exponentials. Instead, this nu and lambda are unknown functions of t and r. Okay. Now, for this metric, for this diagonal metric, is actually relatively easy to compute the curvature, the Riemann curvature, and Ricci tensor and Ricci scalar, and therefore the Einstein tensor. it's even relatively easy to do it by hand. And the answer, so let me just write some of the components for the Einstein tensor. So remember that the Einstein tensor is related to the Ricci tensor in the following way. So R is the Ricci tensor, R mu nu is the Ricci tensor, and R is its trace, is the Ricci scalar. So R is G mu nu, R mu nu. Okay, and then R mu nu, we know that it is given in terms of the Riemann. Riemann we can calculate given the metric. We calculate the Christophers and take derivatives and so on. So we can go through the exercise and find the components of this Einstein tensor. So now I write some of the components which are relevant. So if I compute GTR, that is given by lambda dot divided by R. GTT is given by e to the nu minus lambda prime divided by R minus 1 over R squared plus e to the nu over R squared. And then G RR is equal to nu prime over R plus 1 over R squared minus e to the lambda over R squared. So as you see, it is relatively manageable. And I don't need to write, for now, I don't need to write the theta and phi components of the Einstein tensor. So now if we are looking for a vacuum solution, so vacuum means that T mu nu is equal to 0, and therefore G mu nu, the Einstein tensor, is equal to 0. So we have to set to 0 these quantities. This is equal to 0, this is 0, and this is 0, right? So now what does this equation tell me? Well, this one tells me that lambda is actually just a function of R. It doesn't depend on T. Then we can combine these two equations. These two equations, we can combine them in the following way. We can take e to the lambda minus nu times G TT plus GRR. So if we add them up, of course, this is equal to 0 because GTT and GRR are both 0. But this is also equal to nu prime plus lambda prime divided by R. So what this tells me is that nu, which is generally a function of T and R, is equal to minus lambda of R plus a function of only T, a function that does not depend on R. So let's call it nu tilde of T. Any questions so far? Okay. So now let us again remember how the metric looks like. So now I have, we have discovered that here this lambda is just a function of r, and this nu is separable. It's a function of r plus a function of time. But if it is separable, then what I can do is that, let's see if we can do it here. Okay, so let me use this technology. So if it is separable, if I have e to the, so if I have e to the, so remember nu was minus lambda plus some lambda tilde of t. So we have e to the minus lambda of r. So here I'm writing this fact. E to the minus lambda of r plus mu tilde of t. Or if I want to write the full thing, is minus e to the minus lambda of r plus nu tilde of t dt square. But then if we have this metric, then what we can do is that we can go to a new variable, new time variable, where this factor is just absorbed. So actually, let me write it in a different way. Lambda of r e to the mu tilde of t. So we can just choose a different time variable. By just redefining time, which is another coordinate transformation, in terms of which this metric looks like this. In other words, in a t tilde variable, nu is just a function of r. And then I'm gonna drop this tilde. So let's just call this t tilde variable t. And note that nothing else changes, because I'm just making a redefinition of time. So anywhere else, nothing depends on time. This part, this lambda is really just a lambda of r. There is no t dependence. So by this change of variables, the only thing that I do is that I make the temporal part of the metric t independent. So therefore, under the change of variable t going to t tilde and then renaming it to t, rename. Under doing all of these things, we will get nu is equal to minus lambda. And these are just functions of r. Okay, then finally, so now we learned that nu is minus lambda in this new coordinate, time coordinate. Now we can just solve this equation. Well, we could even solve it before, but now we know that once we know lambda, we know everything. So we just solve this equation. This is first order ODE, very easy to solve. The answer is log of something. Once we plug it inside the metric, we will get the famous Schwarzschild metric. Okay, any question?
Professor,
Yes.
in this metric that you write, again we have a singularity. So in this procedure of changing variables, I mean, we have to write another transformation to make we have to choose another coordinates to make the metric without the singularity or not?
Yes. Yes, this metric has a singularity at r equals rg. And now I guess you wouldn't be surprised if I tell you that this is just the coordinate singularity. And we can actually find a different coordinate system which goes beyond that point. And we will find it in the future. So for instance, if you calculate the curvature of the metric of the manifold or derivatives of the curvature, at that point you will see that they are all finite. So the singularity is not really physical, it's just the coordinate singularity.
Thank you.
Mm-hmm. Okay, so let me make a comment about the fact that so you see something interesting happened, which is that once I impose spherical symmetry and also as impose T mu nu equal to 0, so vacuum solution, I have uniquely fixed so spherical symmetry plus vacuum that uniquely fix the solution metric up to one integration constant. Maybe I didn't mention this. So this RG, so you see what we did was that we solved this equation, right? This is a first order differential equation. So it has one integration constant. That RG that I have here, that is the integration constant of that equation. So the assumption of a spherical symmetry plus vacuum that has fixed the solution up to one integration constant. Now this is kind of similar. It should be familiar from electromagnetism. So there a similar thing happens. If you assume a spherical symmetry, if you consider Maxwell equation and you assume a spherical symmetry and set all sources to 0, you will find the most general solution to be described by a single parameter, which is Q, the charge, the monopole charge. So you get just the electrostatic solution with the parameter Q, which is the integration constant. The fact that the solution is uniquely fixed in this case up to this integration constant, it's a consequence of the fact that we do not have any spherical symmetric electromagnetic or gravitational waves. and that is itself a consequence of the fact that photons and gravitons are massless particles with non-zero spin or with non-zero helicity. So electromagnetic waves and gravitational waves, they are transverse waves. So you cannot have a spherical symmetric configuration of this transverse wave. So this is the result of gravitons being massless spin 2 particles. This, by the way, this is also called, this property is also sometimes called Birkhoff theorem. Birkhoff's theorem. Okay, this was one comment. Well, I guess the other thing that we can do is that we can consider the Newtonian limit. Newtonian limit. So far we consider vacuum solutions, and we set T mu nu equal to 0. Now we can imagine, so therefore this solution is valid outside any spherically symmetric distribution of matter. It doesn't have to be vacuum everywhere, because we just solve these equations, these local differential equations. So even if we have sources, if we go outside those, so if we have localized sources and we go outside those localized sources, this solution is valid there. Now we can consider a model for those sources, a simple model like a star. Consider a static time-independent star, which is a spherical symmetry. And let us also, for simplicity, assume that this star is non-relativistic. Then we can again try to solve these equations in the presence of those sources, which, so now I want to assume that there is a non-relativistic static, and of course the spherically symmetric star, which means that if, given that I'm saying it is a static, it means that we can choose a coordinate system in which T mu nu, well, T0I is equal to 0. So this is the consequence of being a static. And then the consequence of being non-relativistic is that Tij are much smaller than T00. So the pressure is much smaller than the density, mass density, and the mass density is just dominated by the rest mass. So T00 is just rho, the density of the rest mass, or yeah, the if you like, if it is made of baryons, it's just mass of the baryons times the baryon number. So now we can again solve those equations. Another implication of being in the non-relativistic limit is that the metric G mu nu, or there is a coordinate system in which the metric is close to Minkowski metric. So the curvature is small, the gravity is weak. Now, this coordinate system, these are all the statements that there exists a coordinate system for which the T mu nu looks like this. There exists a coordinate system in which metric is close to eta mu nu. This coordinate system is actually coinciding with the one that we were considering before, because if you remember, we found a metric outside the source which was static, which was time dependent and diagonal. And that metric, now we are saying in the non-relativistic limit, that should be in which the sources are small, that metric has to be close to Minkowski, which means that we can expand it. We can expand it to linear order in our variable nu and lambda. So now I can repeat the same procedure. So write the Einstein equation. So if I write the TT component of the Einstein equations, 8 pi g rho equals GTT, then if I linearize that with respect to nu and lambda, I get 1 over r squared lambda plus r lambda prime plus order nu squared and lambda squared and nu lambda. And then we need another equation. So now is the time that one actually needs to calculate the theta and phi component of the equation to look at the trace of the Einstein equation. So the trace of the Einstein equation is r, gives me r equals minus 8 pi g times T mu mu, because the trace of the Einstein tensor is minus the trace of the Ricci tensor. It's minus the scalar Ricci. And again, this equation, if I linearize, I will get 2 lambda over r squared, or let me write it in a better way. I will get twice lambda plus r lambda prime divided by r squared minus mu second plus 2 over r nu prime. So that is r. This is equal to the trace of T mu mu, which in this non-relativistic approximation is just 8 pi g e to the minus nu rho. Again, if we linearize in nu, then this 8 pi g times rho itself is a quantity that I should think of it as being a linear quantity. So I can ignore this e to the minus nu here. So this will be given by 8 pi g times rho in this linearized approximation. Then I can use these two equations, this equation and this equation. If I combine them together, then I will find basically the Poisson equation. I will find nu second plus 2 over r nu prime is equal to 8 pi g rho. Why? Because this term here from this equation, that term is twice or 16 pi g. So this term is just 16 pi g rho. So I substitute it here from there, and then I get this equation. Whose solution is of course the familiar answer for the Newtonian potential. If we remember that nu in the non-relativistic approximation, nu is just twice the Newtonian potential. And m is just the integral from 0 to infinity of rho times 4 pi r squared d rho. So in the non-relativistic approximation, this Schwarzschild solution is just giving me the reduces the Newtonian solution. So in this approximation, you get the usual Keplerian orbits around this body of matter, around this star. Okay, this is everything that I wanted to say today. Any questions?
One question. This mass that we write here, the integral is from 0 to infinity or from 0 to the radius of the...
Oh, it's from 0 to the radius, but you can imagine that you just define rho to be 0 beyond the radius. Or the rho might not be exactly 0, it might decay exponentially outside with some characteristic radius. Okay, so the question is here, why did I approximate this? Why did I approximate this with 8 pi g rho?
Yes.
The reason is that, the reason is that look at here. G times rho, or let's do, okay, so let us just see how this variable, what is the structure of this equation. So on the one side of this equation, you have expressions which look like a second derivative of nu with respect to r. Or if I want to just make an estimate, I can say that the left-hand side of this equation is of order nu divided by r squared, right? So this equation tells me that nu is of order g rho times r squared. In fact, a more precise way of saying that is this, right? M is the volume integral of rho. So an integral which is r squared dr, so it's r cubed, it's volume times rho, and then it's divided by r, right? So now imagine if I kept the next term here, that would be a term over the nu squared.